Here, let's move on from multiplication to division. Give us a 3-digit number
369
divided by a 1-digit number. 5. That should be 73.8. Let's try a 4-digit number divided by a 1-digit number. 3,981 divided by 5. Oh, we just did 5. That's 796.2. Here, let's do give us another 4-digit number.
7,856.
7856 divided by a different 1-digit number, not 5 this time.
7.
7. Okay, that is going to be 1,122.285714. Good. All right. In this lecture, we explore the last fundamental operation of arithmetic, namely division. Just like with mental addition, subtraction, and multiplication, we'll do mental division from left to right. Since you were probably taught to do division on paper from left to right, as far as I know, there's no other way to do division, you will find our basic technique to be similar, but not quite the same as what you already know. But I promise to show you some nice surprises for doing division problems, converting fractions to decimals, and determining if one number is divisible by another. In most applications, we're dividing by 1-digit numbers, so we'll concentrate on those, although I will give you some shortcuts for 2-digit divisors. In a later lecture, I'll show you a very interesting way to do 2-digit division. Before we do actual division problems, let's ask a more fundamental question. When does one number divide evenly into another? Once we've mastered this skill, we'll see how it can be applied to simplifying many types of division problems. Here are some of the tricks that I use. Sometimes you can tell just by looking at the last digit. For example, a number is divisible by 2 if and only if it ends in 0, 2, 4, 6, or 8. It's divisible by 5 if and only if the number ends in 0 or 5. And a number is divisible by 10 if and only if it ends in 0. These are based on the fact that we work in base 10, and 10 is divisible by 2 and 5. Likewise, since 100 is divisible by 4, a number is divisible by 4 if and only if its last 2 digits create a multiple of 4. For example, 271828. Is that a multiple of 4? Well, you only have to focus on the last 2 digits. 28. Is 28 a multiple of 4? Yes. So therefore, your original number was a multiple of 4 as well. How about 1, 2, 3, 4, 5, 6? Is that a multiple of 4? You just listen for the number 5, 6. And since 5, 6 is a multiple of 4, it's 4 times 14, so is 1, 2, 3, 4, 5, 6. Why does this work? Well, to take the number 1, 2, 3, 4, 5, 6 as an example, that's equal to 123,400 plus 56. And since every multiple of 100 is divisible by 4, and 56 is divisible by 4, then so is their sum. By the same logic, a number is divisible by 8 if and only if its last 3 digits create a multiple of 8. Is 1, 2, 3, 4, 5, 6 a multiple of 8? Well, it depends on whether or not 4, 5, 6 is a multiple of 8. And since 4, 5, 6 is a multiple of 8, it's 8 times 57, then so is the original number. How about 31415,926? Is that a multiple of 8? Well, it depends on whether or not 926 is a multiple of 8. But hang on a second. Notice that 926 is not a multiple of 4. I can tell that just by looking at the 26, right? That's not a multiple of 4. So 926 isn't a multiple of 4, so it can't be a multiple of 8, and therefore the original number is not a multiple of 8. Likewise, 1, 2, 3, 4, 5 is not a multiple of 8 since it's not even. Okay, how about multiples of 3? Magically, a number is divisible by 3 if and only if its digits sum to a multiple of 3. For example, 1, 2, 3, 4 sums to 10, which is not a multiple of 3, so 1, 2, 3, 4 is not a multiple of 3. But the digits of 1, 2, 3, 4, 5 add to 15, and that is a multiple of 3, so 1, 2, 3, 4, 5 is a multiple of 3. The number 9 has the same property. A number is divisible by 9 if and only if the digits add up to a multiple of 9. So 1, 2, 3, 4, 5 adds up to 15, which is not a multiple of 9, so therefore 1, 2, 3, 4, 5 is not a multiple of 9. But 2, 3, 5, 8, those digits sum to 18, and that is a multiple of 9, and therefore so is the number 2, 3, 5, 8. Now, the reason these rules work is based on the fact that 9 is 1 less than our base 10. You only need to know about base 10, but if we were working, for example, in base 16, which some computer programmers use, then the same digit sum properties that we saw for 9 would instead work for 15 and its divisors 3 and 5. Funny things happen when we are 1 more than our base. In base 10, a number is divisible by 11 if and only if, when you alternately subtract and add the digits, you get 0 or a multiple of 11. That's a little redundant because 0 is a multiple of 11. So, for example, 8, 4, 3, 6, 8, 9. Is that a multiple of 11? We calculate 8 minus 4 plus 3 minus 6 plus 8 minus 9, which happens to be 0, and therefore the number is a multiple of 11. On the other hand, a number like 5, 4, 3, 2, 1 is not a multiple of 11 because 5 minus 4 plus 3 minus 2 plus 1 is 3, and that's not a multiple of 11. So far, we've discovered divisibility rules for 2, 3, 4, 5, 8, 9, 10, and 11. We're missing 6, 7, 12, and higher. Now, 6 and 12 are easy. A number is divisible by 6 if and only if it's divisible by 2 and 3. And a number is divisible by 12 if and only if it's divisible by 3 and 4. So the only small number left to look at is 7, which is more complicated. One way to check divisibility by 7 is like this. Take off the last digit, double it, then subtract from the rest of the number. That's a lot. Let's look at that slowly. If I have a number like 112, we're going to take off the last digit, we're going to take off the 2, double it to 4, and subtract it from the rest of the number. 11 minus 4 is 7. The original number is a multiple of 7 if and only if the new number is a multiple of 7. Since 112 reduced us to the number 7, then 112 is a multiple of 7. Here, let's test a new number. Let's try 2, 3, 4, 5. Okay? We remove the last digit, which is 5, double it, which is 10. 234 minus 10 is 224. So our new number is 224. Is that a multiple of 7? I don't know. Let's do it again. We've got 224. We'll take off the 4, double it to become 8. 22 minus 8 is 14. And that's a multiple of 7. So the original number, 2, 3, 4, 5, was also a multiple of 7. All right, here's a question. Can your birthday ever be on the same day 2 years in a row? What does this have to do with sevens? Well, the number of days between your birthday is 365 or 366, so it can only be on the same day if either of those numbers is a multiple of 7. So is 365 a multiple of 7? Well, we'll take 36, subtract double 5, 10. 36 minus 10 is 26. Nope, that's not a multiple of 7. How about 366? We take 366, take off that 6, double it to get 12. 36 minus 12 is 24. Nope, that's not a multiple of 7 either. Therefore, your birthday changes each year. Now, I won't go into the reason of why this special rule works here. It uses the mathematics of modular arithmetic, but it's an easy rule to forget. So instead, I like to use a rule that's almost as simple, easier to remember, and can be used for numbers besides 7. The rule I call is create a 0, then kill the 0. Here, we add or subtract a multiple of 7 so that you get a number that ends in 0. Then you ignore the 0. And the original number will be a multiple of 7 if and only if the new number is a multiple of 7. I definitely need an example or two here. Let's test the number 1, 2, 3, 4. All right, 1, 2, 3, 4. Now, how do I create a 0? I need to add or subtract a multiple of 7. Well, 14 is a multiple of 7. If I subtract 14 from 1, 2, 3, 4, I get the number 1220, 1,220. I've now created a 0 at the end. We kill the 0 at the end, leaving us with 122. Now, is that a multiple of 7? Well, you might not know, so let's create a 0. Let's add 28 to that, because 28 is a multiple of 7. 122 plus 28 is 150. You created a 0, now kill the 0 to get 15. Is that a multiple of 7? No. Therefore, the original number is not a multiple of 7. The nice thing about the create a 0, kill a 0 rule is that it can be used for any odd numbers that are not multiples of 5. For example, let's see if the number 2001 is a multiple of 23. All right, so I have to add or subtract a multiple of 23 to the number 2001 to create a 0. Let's see, if I want to add something that ends in 9, 23 times 3 is 69. 2001 plus 69 is 2070. We created a 0. We now kill the 0. By the way, you can only kill zeros at the end. I can't kill that 0 in the middle of 207. All right, I'm looking now at 207. Let's create another 0 by adding 23. 207 plus 23 is 230. Kill the 0 to get 23. Yes, 2001 is a multiple of 23. In fact, it's 23 times 87. But how would you actually do the division of 23 into 2001? I'll show you how to do a problem like that soon, but let's first look at one-digit division. When I was a kid, I remember doing lots of one-digit division problems on a bowling league. If I had a score of 45 after 3 frames, I would divide 45 by 3 to get 15 and would think, at this rate, I'm on pace to get a score of 150. All right, let's consider the problem 79 divided by 3. On paper, you might say 3 goes into 7 twice, subtract 6, then bring down the 9, and so on. But I do it slightly differently. Instead of subtracting 6 from 7, I think of subtracting 60 from 79. Mentally, it looks like this. It's a small change, but an important one. I think, okay, 3 goes into 79 20 times. 3 times 20 is 60. And at this point, I can say the 20. I can say part of my answer. Okay, so I've said the 20. Now, where were we? 79. 3 times 20 is 60. 79 minus 60 is 19. I now have a simpler problem. How many times does 3 go into 19? 3 goes into 19 6 times with a remainder of 1, so there's my answer, 26, with a remainder of 1, or if you prefer, 26 1/3. Let's apply this technique to the problem of converting 76 degrees Fahrenheit to Celsius temperature. To convert from Fahrenheit to Celsius, you subtract 32, then multiply by 5/9. With 76 degrees, we subtract 32 to get 44, multiply it by 5 to get 220, and then divide by 9. So our problem is 220 divided by 9. Now 9 goes into 22 twice, so 9 goes into 220 20 times. So I can go ahead and say the 20. Next I do 9 times 20, which is 180. Subtract that from the 220 to get 40. Okay, now I have a simpler division problem. I'm dividing 9 into 40. 9 goes into 40 4 times with a remainder of 4, so I can say the rest of my answer, 24 and 4/9, about 24.5 degrees Celsius. Now let's try dividing a 3 or 4-digit number by a 1-digit number. Suppose you just won a jackpot of $777. That's the good news. The bad news is it has to be split 4 ways. Let's do that problem in our head. 4 into 777. Well, 4 times 100 is 400. 4 times 200 is 800. That's too big. So go ahead and say the 100. 4 times 100 is 400. Subtract that from 777. So now you have a new problem, 377 divided by 4. Now let's see, 4 times 9 is 36. So 4 times 90 is 360. Okay, so I can go and say the 90, right? I've now said 90. 377 minus 360 is 17. You have an even simpler division problem. Do 4 into 17, that goes into it 4 times with a remainder of 1, and there's your answer, 194 with a remainder of 1, or $194.25 is your share of the jackpot. Let's do the problem 1, 2, 3, 4 divided by 5. Now there are 2 ways we can do this problem. By the method we just learned, we can go through our process and get 246 and 4/5. But I want to show you an even easier way to do this. If we double both numbers in a division problem, the answer will stay the same. So here we have a problem 1, 2, 3, 4 divided by 5. That's the same as 2, 4, 6, 8 divided by 10. And dividing by 10 is real easy. That's 246.8, and that agrees with our previous answer. All right, now let's do some 2-digit division. When doing this, we'll see how our rapid 2-by-1 multiplication skills will really pay off. Let's determine your gas mileage if your car travels 353 miles on 14 gallons of gas. In other words, we'll divide 353 by 14. Okay, now 14 goes into 35 twice, so 14 times 20 is 280. Go ahead and say the 20. Subtract 280 from 353 to get, 353 minus 280. You might subtract 300 and add 20 to get 73. And now we have a simpler division problem. 14 into 73, how many times? 5 times. 14 times 5 is 70, so we can say the rest of our answer. You'd be get 25 with a remainder of 3. You'd be getting a little more than 25 miles per gallon. Now let's consider the problem 500 divided by 73. Okay, so first we have to ask, how many times does 73 go into 500? It's natural to guess 7. But 7 times 73, when we do that 2-by-1, we get 511, which is a little too big. At least we know that our quotient is 6. Okay, so we do 6 times 7, so we can say the 6. We can then do 6 times 73 to get 438. What's 500 minus 438? By complements, we know it's 62. So there's your answer, 6 with a remainder of 62. But we could have done this problem another way. Remember when we tried 73 times 7 and we got 511? Too big, right? Well, we can actually take advantage of that calculation. That didn't have to go to waste. You could actually think of your answer. Don't say it, but you could think of your answer as 7 with a remainder of negative 11. Now that sounds a little ridiculous, right? But that's the same as an answer of 6 with a remainder of 73 minus 11, 62, and that agrees with our previous answer. So why does that work? Because 500 is 73 times 7 minus 11. And when we replace 7 with 6 plus 1, we actually get 73 times 6 plus 62. I call this technique overshooting. Sometimes in a division problem, I will deliberately overshoot. For example, let's do the problem 770 divided by 79. Now we know that 79 times 10 is 790, but go ahead and think it anyway. 79 times 10 is 790, and that's too big by 20. So the answer that you think is 10 with a remainder of negative 20, and the answer you say is 9 with a remainder of 79 minus 20, 59. Okay, let's try a 4-digit number divided by a 2-digit number. This is about as large a division problem that most people can handle, even with practice. Consider the problem we saw earlier, 2001 divided by 23. Okay, now let's see. 23 times 8 that's a 2 by 1, it's 184. 23 times 9 is 207, that's too big. So we start by saying 23 times 80 is 1,840. Okay, so you can say the 80, get that out of your memory, and now you have to subtract 2001 minus 1,840. Now, how far is 1,840 from 2001? Now, if you use complements, you know that 1,840 is 160 away from 2,000. So how far is it away from 2001? Just add 1 to it, 161. Okay, finally, we have to divide 23 into 161, but 23 times 7 is 161 exactly, so there's the rest of your answer, 87. If we change that problem by just a little, it becomes actually easier. Let's look at the problem 2012 divided by 24. We see that both numbers here are divisible by 4, right? Because 12 is divisible by 4, 24 is divisible by 4. Specifically, 2012 is 503 times 4, and 24 is 6 times 4. So you could do 2012 over 24, and that simplifies to the problem 503 divided by 6. Thus, we've reduced our 2-digit division problem to a 1-digit division problem, which is easier to do. When doing the division 503 divided by 6, we get an exact answer of 83 and 5/6. But the answer to the original problem is not 83 with a remainder of 5, but it is 83 and 5/6. The reason for that is we divided both of our original numbers by 4, so the real answer would be 83 with a remainder of 20, or 83 and 20/24, but that's the same as 83 and 5/6. As long as we express our answer in terms of a fraction, we'll be okay. Here, let's try the problem 314 divided by 16. Since both numbers are even, we can divide both numbers to give the new problem 157 divided by 8. And since 8 times 20 is 160 is a little too big by 3, we can get an answer of 20 with a remainder of negative 3. That's what we think. Then we think that's 19 with a remainder of 5, but we have to say the answer 19 and 5/8. When the divisor ends in 5, doubling both numbers will usually simplify your problem. For example, 695 divided by 25. If I double those numbers, I get 1390 divided by 50. Ooh, let's kill both zeros to get the problem 139 divided by 5. Hey, there's a 5 again, so let's double both numbers to get 278 divided by 10, and that's our answer, 27.8. When dividing with decimals, I try to turn it into an integer problem if I can. For instance, 3.45 divided by 1.2, multiply both numbers by 10 to get 34.5 divided by 12. And then to get rid of that 0.5, let's double both numbers to get 69 divided by 24. But hey, both of those are multiples of 3, so let's divide both numbers by 3 to get 23 divided by 8, and that's equal to 2 7/8. For all of these division problems, I've been expressing the answer using a fraction at the end. But sometimes we want to convert the fraction into decimals. When the denominator is 11 or below, it's extremely easy to compute the decimal expansion. You probably already know the decimal expansions when the denominator is 2, 3, 4, or 5. I'll display them here. I didn't list 2/4 since it's the same as 1/2. Naturally, when the denominator is 10, the fractions are automatic. 1/10 is 0.1, 2/10 is 0.2, and so on. The fractions with denominator 6 and 8 are worth memorizing since they often arise in measurements. And once you know that 1/9 is 0.1111, then we instantly have the others. 2/9 is 0.2222, 3/9 is 0.333, and so on. Likewise, 1/11 is 0.090909 repeated. Once you know that, you know all the others. 2/11 is 0.1818 repeated. 3/11 is 0.2727 repeated, and so on. The fractions with denominator 7 are the trickiest, but they're also the most interesting. The fraction for 1/7 is worth memorizing. It's equal to 0.142857 repeated. That is, it's 0.142857, 142857 going on forever. If you draw these numbers in a circle, it looks like this. This decimal expansion is especially easy to remember because it starts with 14, then doubles to 28, then nearly doubles again with 57 before repeating. What's cool is that once you know this fraction, you know all the other sevenths fractions too, right? So looking at our circle of 142,857, check this out. All right, 2/7 is going to start with the 2 and then go around the circle forever. It's 0.285714 repeated. And 3/7 is 0.428571 repeated. 4/7 is 0.571428 repeated. 5/7 0.714285 repeated. And 6/7 is 0.857142 repeated. And it's easy to know where to start on the circle if you remember that 1/7 is about 0.14. So 2/7 is going to start 0.28. 3/7 is going to start 0.42. 4/7, well, let's see, 4 times 14 is 56. It doesn't start 0.56. There aren't any 6's on the circle, but it starts 0.57. 5/7, well, 5 times 0.14 is 0.7, and we start with the 7. And 6/7, 6 times 0.14 is 84, and we start with the 0.85. Take a minute to study this circle. It'll be well worth it. Okay? Memorize this, and then I'll ask you a couple of questions. Okay, most importantly, what's the decimal expansion for 1/7? It's 0.142857. No, don't look at the circle either. Okay, how about 3/7? What's that going to be? 3/7 is, well, it's going to start with 0.42, so it's going to be 0.428571 repeated. And 6/7, see, 6 times 14 is 84. It starts with the 8. It's 0.857142 repeated. When dealing with fractions with larger denominators, we treat it as a normal division problem, but we can occasionally take shortcuts, especially when the denominator is even. For example, consider the fraction 3/16. Now, we begin in the usual way, except we start with a decimal point, and then 16 goes into 30 once, it's 0.1, we can say that. 30 minus 16 is 14, and now we have a new division problem, 14 divided by 16. But we know that 14/16 is the same as 7/8, and 7/8 is 0.875. So you can now say the rest of your answer, 0.1875. Here, let's do the fraction 5/14. Okay, so we start by saying decimal point. Then 14 goes into 50 3 times. Go ahead and say the 3. 50 minus 42 is 8. And you're left with doing the division problem of 8 divided by 14. But 8/14 is 4/7, and you know 4/7, right? That's 0.571428 repeated. So if you really want to impress your friends, you'll say the answer, 0.3571428, 571428, and so on. With odd denominators, you may be out of luck, unless the denominator is a multiple of 5, in which case you, like we've done with 5s before, you can double the numerator and denominator to make the problem easier. Like 11/15, think of that instead as 22/30. And now 22/3 is 7 1/3, 7.33, so 22/30 is going to be 0.733 repeated. We've covered a lot of ground in this lecture. Here are some of the strategies that we've learned. We looked at divisibility tests for all the numbers from 1 to 12, and even beyond those by using the create a zero, kill a zero method. These tests are valuable for simplifying your division problem before it even starts. We divide numbers from left to right using a process similar to long division, but we say our answer as we go along and we simplify the problem as we go. The process can sometimes be further simplified by overshooting occasionally. It's easy to convert fractions to decimals, especially with one-digit denominators. And as we saw, dividing by 7 is especially interesting. There were many new ideas, and if you practice these techniques, you'll be dividing and conquering numbers in your head in no time. We've now covered the fundamental techniques of mental addition, subtraction, multiplication, and division. What comes next? Although developing an ability to find an exact answer is the foundation of all mental math, sometimes all you really need is an estimate, especially when the problems are large, but in many other situations too. So, in our next lecture, we'll explore the art of mental estimation. Here, we don't need the exact answer, so we can do these problems even more quickly and still be pretty close. It should be pretty good.